Okay, so let's get started. So before we, so last time we had a breakout room discussion on matching methods, okay, I'm recording my video, and today before we would delve into that, I'd like to tell you that the homeworks are graded and posted online with solutions. So if you have any questions, let me know. And also, I got created a midterm feedback form using some of the tools provided by the university. So feel free to use it and give me some feedback so that we can, further improve this course for the rest of the quarter. And the link is here, but also on Canvas site. So you can log on to Canvas and you'll see where to get it. So that's that. Any questions from our discussion from the last time? So what I plan to do now is that, so last time we break out into groups and discussed different ways to match observations. And today I'd like to hear from each of you or each of the groups on their ideas. What are the considerations when you're constructing a matched sample, and what are, what are your proposed solutions for this particular toy example? So what I'm going to do is that, first of all, I'll give you the link to the same worksheet that we did last time, and I'll give you 5 minutes to go back to your breakout room and discuss with your peers, since it's been a couple of days, discuss with your peers, what are the considerations you talked about, what are the solutions, what are the things you want to share with the class when we get back. So I will open up the breakout rooms and you will choose your rooms. So go back to the room that you were assigned before. If you wasn't here last time, I think all of you were here last time. But if you wasn't here, you feel free to hang out in the main room and we can chat. So I plan to have you back in 5 minutes. Josie, see that your friends are not here.
Oh, sorry. I forget.
Yeah, Olivia and Mary are not here today, so I guess you will be taking full responsibility for what you have discussed.
May I jump to other room?
Yeah, if you whichever you prefer, you can jump into other rooms, or I can go to one of these rooms and introduce you, or if you would prefer, you can take a 5-minute break. So depend on your preference. You can let me know what you choose.
Yeah, either one. Can you assign me to either one room and we can discuss?
Okay. So I'll assign you to maybe room 1.
Sure.
So let's see. Join.
Okay, thank you.
Hello. Welcome back. Is midterm happening this week? I have no idea. Do any of you have like midterm exams?
I have one next week.
Okay. Let's see. And you're Rachel, you're year 2, I believe.
Yeah.
Okay. So we'll just wait 1 more minute so that they'll come back. Feel free to take a 50-second break, or if you have any quick questions, you can shoot now. Okay, so now we have everyone back. I'd like to hear, is there any volunteer that wanted to share their thoughts? What are the considerations in coming up with a match? Someone from group 1, maybe?
Sure. Yeah, I think the considerations, I mean, we didn't really formalize this in our matchings, but coming up with some sort of distance metric that you would want to minimize the distance between the matches. So you'd have to weight each category somehow, or each variable somehow. Hopefully based on some, background knowledge about what you know is important to prioritize your scientific knowledge.
Thank you. Yeah, that's a good point. Any other thoughts, or does anyone want to tell me a proposed solution of, or a proposed matched sample? Anyone from group 3?
Yeah, maybe I'm going to present.
Okay.
Okay,
Yeah, so let me just scroll over to your, okay.
Yeah, we consider many scenarios, but before we go to each scenario, we're gonna first encode the table by splitting the variable into 2.
I see.
That is in page 10. You can see that we encode male using number 1 and female using number 0. And later we consider 4 scenarios. So for the first scenario, for each individual, we check their sex and match each individual in the treatment group to find one sample from the control group with the same sex with that individual. And then we match the individual by minimizing minimizing the difference in their age. So a example for scenario 1, that is, so for the first example, for the first individual in the treatment group, which is ID 1, we then match him with the sample with ID 6 in control group, because they have same sex and their age could be a little bit smaller, but it could be not very significant in that case. But if we look at the second sample in the treatment group, which is 0 in sex, and we found that the sample 5 in control group, which has the same sex, but their age could be very close. And we do the same thing for the remaining samples in the treatment group, and so on and so forth. So we match the sample 3 with the sample 6. It's like they have very trivial difference in their age, but they have same sex.
Mhm.
Yeah, that's
I see.
our idea here. And for scenario 2, that is pretty much the opposite of the scenario 1. So we first match we first match their age and then
Mhm.
consider the sex. So we have priority at here for
Mhm.
these two variables. But for the first two scenarios, it's kind of a step-by-step methodology, which is not a little bit, can be criticized by someone because it's like conditioning on the selection of the first variable while we do minimizing difference in the second variable, but this is kind of not a simultaneous work. So in scenario 3, we consider by minimizing the difference by considering two variables at the same time. It requires that we need to standardize each variable so they can be on the same scale. But at here, the problem is, for sex, it is kind of a categorical variable. It's a little bit hard to measure the difference in the Euclidean scale. So this question remains open, even though after we finish our discussion, but so this question could be still a little bit hard to answer. So we cannot find a very good answer to this question. And for scenario 4, that is more like a remedies for this kind of matching, because if we match one individual with in treatment group and one individual in control group, this kind of, we have some individuals to be left off. Just in this example, we have maybe like one individual to be left off in a control group. So maybe we can consider some one-to-many matching, maybe using some of the above methods. Like maybe a example I can give could be like, you can consider a Westerstein distance is somehow like some like kind of idea. I'm not sure if it works.
Okay. Yeah. Thank you, Tianchen. Yeah, thank you, Group 3. Yeah, that's a lot of good considerations. And so, yeah, I was going to ask why you're matching ID number 3 with 6, but not with 7, since they're all both very similar. But then later on, you said that there's also this idea of matching multiple controls to a single treatment, which I think kind of answers my question. So I'll quickly type down some of the things that you mentioned, while I'll give time for those who haven't spoken. If you want to chime in, feel free to do so after I finished typing. Anyone else wants to add anything? Okay, so if none, then yeah, good work, everyone. Let's continue with our lecture. Okay, so you have discussed a lot of great ideas, and before we move on to discuss a lot of the more detailed considerations, many of those have been brought up. We'll first look at take a digress to look at one other thing called balancing score. And we'll see that this you will see that this has close connection with how do we find matches. Okay, so as many of you have said, the reason to when you're looking at the data, when you want to find matches, you want to look for similar covariates in the treatment group and the control group. And the intuitive reason behind doing this is that if we are able to find perfect match, then for each matched pair, their covariate values will be the same, and one is treated and one is control. So in that case, in the matched sample, we would have as if randomization, simple randomization, or in other words, the treatment is unconfounded or ignorable. So then we can proceed with very simple estimation methods. And we have seen that it's hard to have exact match with many covariates, and even with just 2 in our example, it will be difficult to, or sometimes impossible to find exact matches. So many of you have hinted on this idea of, is there a summary that we can match on? How do you calculate a distance between 2 sets of variables with multiple covariates? And balancing score is one way to summarize the data when considering matching. So here's the definition of balancing score. A balancing score, B of X, so X here is a covariate value, B is a function. So balancing score is a function of covariates such that the treatment assignment is independent of the covariate, conditional on the balancing score, this summary of covariates. So by this definition, you can see that balancing score is not unique. There are many different examples. So for example, if we just take B of X to be the entire X, that is a trivial summary that does not summarize anything. It's the covariate itself. But by definition, A will be independent of X given X. That's some basic probability. So another example would be, suppose the treatment assignment, suppose we know that the treatment assignment is determined solely based on a subset of all the covariates. Suppose it's assigned only based on Zi. Then a subset of X. Then in that case, the balancing score, you can take the balancing score to be Z. And in this case, we'll have A independent of the entire X conditional on Z, the information that determines A. A third example, which is the most relevant for our discussion here, is that we can choose B of X to be the propensity score. So propensity score, probability of receiving treatment given X. And we'll prove that the treatment is independent of covariates conditional on the propensity score. Okay, so why do we care about finding a balancing score, that finding some summary of covariate that satisfy this condition? This is because if we have a balancing score, then we have conditional ignorability, not just conditional on the entire covariate, but we have conditional ignorability given a summary of the covariate, here B of X, the balancing scores. So this is I guess you can call it a theory or a lemma that's resulting from the definition of the balancing score. So this statement means that if we have this function B, then within strata of B of X, which is usually coarser than the strata of X, we have as if simple randomization. So suppose we think about propensity score. It means that for all the people that have propensity score equal to 0.6, let's say, then in that strata, the treatment assignment is ignorable, is independent of the potential outcomes. So when we only look at individuals with propensity score 0.6, we can just compare the group mean difference, and that would be the treatment effect in that strata. No more weighting or standardization or that kind of business. Okay, so why is that? Why do we have this conditional ignorability given the balancing score? This is because intuitively, because within strata of the balancing score, the treatment assignment is independent of X. So let's go through a simple proof for this result. So what we wanted to show is that A is independent of Y0 and Y1 conditional on B of X. You can write out the definition of conditional independence, and we can see that it suffices to show this equality hold. So probability of A equal to 1 given the potential outcomes and B of X is equal to probability of A equal to 1 given the balancing scores. Okay, so let's calculate the left-hand side. So for the left-hand side, probability of A equal to 1 is just expectation of A. So we can use iterated expectation and we get this term. So the iteration is that the inside expectation, we have an additional X. Then in the outside expectation, we integrate that out. Okay, so now, because we have conditional ignorability given X, that's our presumption, the inner expectation, we know that A is independent of the potential outcomes given X and B of X, since it's a function of X, so it doesn't matter. And therefore, the inner expectation equals this. Okay, now, because we have Bx being a balancing score, by definition, A is independent of X given B of X. And therefore, this expectation equals this expectation. So this is what the blue term end up equal to. And therefore, the right-hand side becomes this iterated expectation, but the inside is only conditional on B of X. So because this is this conditional expectation is a function of B of X, and on the outside we have conditional on B of X, so we can pull that, or in other words, you can say this is a constant with respect to this conditional set. So you can get that outside the expectation, which becomes this, and this is the right-hand side. So, any questions for this proof? Or maybe you want to spend some time and look at it. It's quite fascinating how people discovered this in 1983 in a biometrical paper. Okay. So this is a property of a balancing score. Then a second result is that the propensity score is a balancing score. So which means, effectively is telling us that we only need to looking at the strata of the propensity score, and then we will have conditional ignorability, or we have ignorability in that strata. Okay, so this is a result saying that the propensity score is a balancing score. In other words, by definition, treatment is independent of the covariates given the propensity score. And here's the proof. The proof is, again, just a few lines. So I'll go through that with you. Again, by the definition of conditional expectation, it suffices to show this equality. Probability of A equal to 1 given X and P of X equal to probability of A equal to 1 given P of X. Okay, so now the left-hand side, what is the left-hand side? Left-hand side is this, but by P of X is a function of X. So you can remove that from the conditional set, which gets us this. And this is, by definition, the propensity score. So the left-hand side equals the propensity score. Now let's look at the right-hand side. The right-hand side, we can use a law of iterated expectation to get a X in the inner expectation, right? From here, we get iterated expectation. This is P of X. This is conditional on P of X and X. And now the inside, as we have shown previously, the inside is just the propensity score, because now the inside is the left-hand side of the equation. So this is just the propensity score. And therefore we have expected propensity score conditional on propensity score, which of course equals propensity score itself. So the left-hand side and right-hand side both equal to the propensity score. And therefore we have the result that A is independent of X given P of X. Now, here the proof, there's nothing special about A being the treatment or X being the covariate. You can have this kind of result for general random variables. You can try to write a version for general random variables, but it just happens that this is the most useful one for our purpose, for the matching. Okay, so what does the results we've derived imply practically? It means that suppose we match, instead of matching on covariates, or based on certain distance measure, or we're kind of combining two covariates together in certain way, it's blah blah blah. Instead of doing that, suppose we calculate the propensity score for each individual, and then suppose we match on propensity score. Then, of course, by definition of a matched sample, we would have balance, or the P of X would be the same for a control and its match, for treated and its match in the control. So we have P of X in having balance between the treated and the control group in the matched sample. And because P of X is balanced between the treated and the control group, we have treatment independent of P of X. Okay. Now, furthermore, this is a result we've shown. A is independent of X given P of X. So combining these two results together, we know that in the matched sample, we have treatment independent of the covariates. So this means that we kind of achieved the goal that we wanted for doing the matching. In the matched sample, we have as if simple randomization. Therefore, we can proceed with very simple estimation methods. Any questions?
How well does this work if you've misspecified P of X?
Good question. I don't know.
Yeah.
I'll need to look into the literature to find out. I don't know, but it should have consequence, of course.
Right.
Yeah.
It just seems like a natural drawback of like you're using a calculated value instead of the actual covariate values, which presumably are more trustworthy.
Yes, that is a good point. Yes. Yeah, so I agree. One shouldn't say, okay, you should always do propensity score matching. But it depends on if you have good confidence in your propensity score model, especially, the more covariates you have, maybe one could say they will have a better chance of getting a good model for the propensity scores. Not the more covariates, but the larger the sample you have, then maybe you will have a better chance of getting a good propensity score model. And in which case, if the number of covariates is also large, then you might want to match on the propensity score instead of the entire set of covariates. But yeah, that's a good point. All these arguments relies on the proof is assuming you know the propensity score. Then in practice, you will need to model it. You need to estimate it. Okay, thanks. All right, so one additional result that we're not going to prove, but I just want to bring it up to you, since it's quite interesting, is saying that the propensity score is the coarsest balancing score. Mathematically, it means that the propensity score is a function of every balancing score. But what it means in practice is that suppose we want to find the, I guess, the coarsest summary measure that we can match on, then propensity score is the coarsest summary measure. In other words, matching on propensity score provides the biggest benefit in terms of reducing the number of variables to match on. But of course, again, it relies on you have good models for propensity scores. Okay, so today we'll look into the detailed steps for conducting a matching analysis, and if we have time, we'll go through some R code. So I'll switch slides, and if you have any questions, this is a good time to ask. Okay. Okay, so this is what we're going to talk about today: implementations and details for the matching method. And in particular, for today, we want to discuss 4 steps. Define the distance measure, implementing a particular matching method, assessing balance, and analysis after finding a matched sample. So these 4 steps: defining distance measure essentially means, how do we determine whether 2 samples, 2 individuals, one from the treated and one from the control, they are similar to each other in terms of covariate value. And some of you have already hinted upon that. You have different types of distance measures that one can use to define the similarity. And from what we have just seen, the property of propensity score, we can also define distance measure based on the propensity score. So the second step is implementation of a particular matching method. So how do we find a matched sample? How do we describe an algorithm to find the matched sample given the particular distance measure? The third step is, after finding a matched sample, how do we assess the quality of the resulting matched samples? Do we achieve balance in covariance? And the final step is analysis of the outcome, or estimation of the treatment effect. So today we'll go through these steps one by one. First, the distance measure. So what criteria do we use to determine if xi from the treatment group and xj from the control group are similar to each other, and hence they can be matched as a pair? So for example, in our toy example that we worked on, how similar are this female 55 years old and this female 50 years old? Or maybe these 2 are more similar, female 55 and male 55. Right? Do we care more about age? Do we care more about gender? So in these cases, the most important one is domain knowledge. I didn't tell you what's the outcome or what's the particular scientific problem that we cared about. So there's no way to tell which one matters more. But in real practice, you will be able to rely on domain knowledge to guide this kind of choices. But regardless, there are some mathematical tools to operationalize these kind of domain knowledge. And so here we'll see a few examples of different types of distance measures. So we'll use dij to denote the distance between individual I and individual j in terms of matching. So Dij captures their covariance distance. So the first one example is exact matching. So the distance is either 0 or infinity. It's 0 if the two covariates are exactly the same, otherwise they're completely different. Now, we've seen this, the use of this distance in, if you still remember, the little red balls and blue balls example that I showed last class. But very often this is not very practical. So another example is this so-called Mahalanobis distance. So what it does is that, so here, if you ignore the sigma inverse for now, then this is a quadratic or squared difference between xi and xj. And the sigma variance, sigma inverse here is to standardize different entries in or different elements in the vector x. So for example, one typical choice of sigma is that it's the variance covariance matrix for the covariate x. Sometimes people calculate sigma using only the controlled sample. So obviously it's easy to see that this probably works the best for continuous outcomes. And if we have mixed outcomes, some categorical, for example, in our example, we have male and female, then it would be more challenging to make sense of this difference. But anyway, this is a commonly used choice. A third choice is the propensity score. So as we have said, propensity score can be used as a balancing score in a sense that if you match on propensity score, you have covariance balance. So, and therefore, people often use the absolute difference in propensity score as a distance measure. Another related one is the so-called linear propensity score. And so instead of taking the difference in propensity score, they take the difference in the logit of the propensity score. And the reason for doing that is that the propensity score lies in between 0 and 1. So it makes many different values seem similar. Whereas if you use the logit transformation, then you stretches the range of the propensity score to the entire real line while preserving the ranks. So now this is all intuitive argument. There's no theoretical justification behind it. But researchers have found that matching on the logit of propensity score is usually more effective in reducing bias in practice. Okay, so one thing I'd like to note is that all these measures are invariant to scaling and shifting. Meaning that, for example, if you measure years in terms of, measure age in terms of years or in terms of months, it doesn't matter. These distance measures will still be the same. The ones on the previous slide as well. And there are also other types of distance measures. For example, if there are a few key covariates that the researcher believes are very, very important to match on, then we can ask for exact matching on these key variables. Then maybe we can use Mahalanobis distance on the rest of the variables. So in the toy example that we went through, for example, we can ask for exact matching on gender, if gender actually is very important. Then we have a, so in this case, it would be the simple difference in age as a secondary measure. So this is actually scenario 1 described by Tianchen, I believe. Okay, any questions? Okay, so now let's go to the second step, implementing a matching method. So what do we mean by implementing? It means that given a distance measure, we want to figure out what is the algorithm we use to construct a matched sample. Now, for this particular example below, having an algorithm or not, that doesn't matter because this is just 9 individuals. We can do it by eyeballing, but it matters for larger data sets. So there are a lot of different algorithms to do this kind of matching. And here we'll go through some commonly used ones. So one of the most common and easiest to understand implementation is the nearest neighbor matching. So here's an example. One-to-one nearest neighbor matching. So essentially it is saying that for each treated individual, we'll match them with the control individual with the smallest distance defined on the in the first step, right? Okay, so this sentence does not completely describe what the algorithm would do. So there are a few considerations. For example, now here I said 1-to-1, but is 1-to-1 the best, or do we want to increase the number of controls matched to each treatment? Or maybe we want to have some variable number of matches for different treated individuals. This is one consideration. Another consideration is, can the same control be matched to multiple treated individuals? Can we reuse the control in constructing the match? Do we want to reuse the control? What are the pros and cons for doing this? Okay. I remember in our example, we have a treated individual, male, 18 years old. And there's someone in the control that is 30 years old. So of course, you might want to match that 30-year-old male to this 18-year-old male, or maybe that's a 30-year-old female, I can't remember. But anyways, you might want to match that control to this particular individual, but that control may also be very similar to another individual. So in this case, do we want to reuse that control? A third consideration is, do we use a greedy algorithm by starting from the first treated? Or do we do something else? Do we aim for some kind of global optimality? We'll see this in more detail later on. The fourth consideration is, what if for some treated individual, the closest control is still very different? And again, going back to our example, we have this 18-year-old male in the treatment group, and everyone in the control group has age greater than 30. So suppose age is an important factor in this particular example, then there isn't really a very good match for this male, 18 years old male. So in this case, do we want to find a match no matter what? Or do we do something else? So we'll briefly discuss each of these considerations. The first one, number of matches. So when there are a large number of control individuals, sometimes it's possible to get multiple good matches for each individual. In which case, especially if the data set is very large and the number of controls is far larger than the treated individuals. In this case, you might want to consider 2-to-1 matching or 3-to-1 matching, etc. So in this case, there is this bias variance trade-off consideration. Here, I did not intend to list the results. I messed up with my presentation slides. But I'll still ask you. So here I said, 1-to-1 matching results in smaller bias, larger variance. Many-to-1 matching results in larger bias, smaller variance. So first, do you agree with it? And hopefully you do, but maybe you don't. And second, can you explain why these are the cases? anyone want to speak up their opinion? To make my question more specific, why am I saying that one-to-one matching tends to have smaller variance compared to, say, two-to-one matching? Suppose we find two individuals from the control for each treated. Now, of course, here we're not talking about estimation yet, so it's kind of ahead of the schedule. But let's see if you have any intuitions behind this. Oh, where am I? Oh, over here. Okay. Anyone want to speak up?
Well, I have an understanding, but might not be correct.
Yeah, go ahead.
So when we consider many to one matching, that is, we find many samples in control group to be matched to one individual in the treatment group. So I'm thinking, like, if you pick one individual from a treatment group, for that X, we cannot find some very exactly matched samples in control group. That is, we have some discrepancy in X, so which might lead to larger bias due to we cannot estimate propensity score very correctly. I'm not pretty sure if it is this case.
So let me see if I get your thoughts. So you're saying that if we do many to one matching, then some of the controls will be used up for the earlier X's, so that for the later ones you will have poorer match. Or maybe I misunderstood.
Sorry, maybe I didn't make it clearly. So I'm thinking, like, if you consider one specific X in treatment group, it is hard to find many X which can be matched to this X in control group. So which might give a very poor estimation.
I see.
Propensity score gives larger bias.
I see. I think I understand what you're saying. So you're saying that if we ask for example, 3 matches in the control group, then some of the matches will be poorer than suppose we ask for only a single match from the control group.
Yes, right.
Okay, good. Yeah, I think that is the understanding here. I have the similar view as you did. So in other words, the more matches we ask for, the less quality in a match that we'll have in terms of covariate being in the control being very, very close to the treated. And therefore we'll have a larger bias. But since by having many to one matching, we kind of increased the effective sample size in our analysis, one would likely have smaller variance. Of course, this is not a fixed rule. This is not always the case in practice. There's usually some kind of sweet spot in terms of the matching ratio. Thank you. So there's also this idea of variable ratio matching, where we can change, we don't have to have a fixed matching ratio. And in this case, in the analysis, you would have to do some kind of weighting to account for the fact that some individuals are matched with multiple controls, where some treated individuals are not. Okay. The second question is with or without replacement. So in other words, do we reuse controls when constructing matches? Can the same control be selected as a match multiple times? So so this with replacement, without replacement, these are just explaining what it means. And I think I've already explained it quite clearly. And in this case, there is also this bias variance trade-off. So if we do matching with replacement, then we would have a better chance that each treated will be matched with the best control. Because the best control, you know, two treated may have the same control as their best match. So if we're able to reuse them, then we'll kind of increase the balance in the matching. If we count the, you know, if we reuse someone, we count it twice. And in this case, we'll have a smaller variant, a smaller bias. But generally speaking, we would also have larger variance because effectively you're reducing your sample size when using when doing matching with replacement. So that I guess this consideration is kind of similar to what we've seen on the previous page, right? It's all about the quality of the match and the sample size. Okay, so now the third consideration is, do we use a greedy algorithm or do we use some different algorithm? So what is a greedy algorithm? In this nearest neighbor matching example, a greedy algorithm is that you start, so you sort the treated, or you order the treated somehow. You have an ordering, then you start from the first treated, select the closest match from the control, then move on to the second treated, and then select the closest match, so on and so forth. So in this case, the order in which the treated are matched matters. In other words, we may not achieve a globally optimal matching when using a greedy algorithm. Now, whereas if there's this other idea called optimal nearest neighbor matching. So instead of going from 1 to 1, we consider minimizing a global distance measure. So suppose consider it to be the average distance in each match, averaged over all the matches. Now, I didn't specify a clear way of how do we achieve this, right? But you can at least think, oh, the most straightforward, but probably computationally expensive way is to enumerate all the possible matches and then find the matched sample that minimizes this global distance measure. So it turns out that, you know, this optimal matching is computationally expensive. It's not feasible for very large data sets. So if the data set is very large, then probably you would end up doing this kind of greedy matching algorithm. And in the R code that we'll see later on, there are places where you can specify if you want a greedy matching algorithm or an optimal matching algorithm. Okay, any questions? If not, let's talk about the fourth consideration. So we asked this question: what if for some treated individuals, the closest control is still very different? What do we do? Do we still find the control anyway, or do we do something else? Now, this is not a definitive answer, but this is, on this slide, I'll provide you a strategy to do something else. One strategy is to impose a so-called caliper and only select a match if it is within the caliper. So, for example, suppose your caliper is the age difference must be within 10 years. Then in our example that we did, the first person, a male 18 years old, does not have any match within this caliper. So in this case, because he does not have a match, he will be discarded from the data set. You can define caliper in different ways. You can define it in terms of the covariate value. You can define it in terms of the propensity score difference, so on and so forth. Now, there's also this trade-off when considering a caliper. So if we impose a caliper, then some of the data will be discarded. Some of the treated individuals will be discarded. So, which means the sample we end up with is no longer representative of those who got treated. So the covariate distribution is different. And this leads to difficulties in interpreting the effects because we've changed the population. But on the other hand, having a caliper can help avoid poor matches. And poor matches can lead to, large bias, can lead to large variance, etc. So I guess what I'm trying to say here is that having a caliper or not is not a difference between a good matching method or a bad matching method, but rather having to impose a caliper indicates that your data is not very good. So it's a matter of good data versus bad data, not good method versus bad method. And caliper is a way to salvage to some extent in the presence of a bad data set. Okay, so besides nearest neighbor matching, there are also other matching methods. There are things called subclassification and full matching, and also other methods. So I won't go into details in here, and here's a nice review paper that if you're interested in, you can go and see these other methods. Okay, so the third step after matching in the matching procedure is to assess covariate balance. So what balance do we care about? We want in the matched sample A independent of X. So as if we have simple randomization in the data. And in other words, we want to be able to see that in the matched sample, the distribution of X in the treated group is the same as the distribution of X in the control group. So ideally, one would want to maybe plot a multi-dimensional histogram if we have a vector of X. A histogram for equal to 1, a histogram for equal to 0. But of course, this is often not practical because if you do this, if you have many X's, then a lot of these cells would have 0 count. So one thing that people usually do is to check for marginal covariate balance. I want to point this out because checking for marginal covariate balance does not imply this independence. You may still have some weird, marginally they're independent, but jointly variables are not independent. But anyway, this is what people usually do in practice. So check balance in each dimension of X marginally. And this is, so I'll for the next few slides, I'll show you some plots that are useful for looking at assessing balance and matching. And the code to do all these plots is uploaded to Canvas as well. So this first one is called a jitter plot. This is not assessing balance and covariate yet. What it does is that it plots the propensity score. By the way, this should be from 0 to 1 because this is a propensity score scale. I believe the author made a typo in this figure in that paper. So this should be 0 to 1. And what this graph is showing us is that, so these are the treated individuals that got matched. These are matched control units, each to each. And then there are some unmatched control units and their propensity score distribution. And it is usually the case that the unmatched control units will have a smaller propensity score because usually usually treated individuals have larger propensity score, controls have smaller propensity scores, and the controls with larger propensity score got matched. So this is jitter plot, but of course it's difficult to look at when the sample size is large. For example, here we have thousands of individuals, and this does not really tell us much. So there are other ways to look at the balance. One way is the standardized mean difference. We have seen this in when we look at inverse probability weighting estimation. We compared the covariance distribution in a weighted sample. So here we can also calculate standardized mean difference for each covariate in the original sample and after matching, after we constructed a matched sample. So as we said previously when talking about this, you can use table 1 or you can do plots to explore the value of standardized mean difference for each covariate. So this is a table 1 example. This is the right heart catheterization dataset that we've seen when talking about marginal structural models. So here's the result. This is the table 1 before matching. This is a control group. This is treated group. These are all the covariates. And what we focus on is this column, SMD. So we see that there are a few SMD values that are quite large. Remember, the rule of thumb is that if it's larger than 0.1, then we consider it imbalanced. So there are quite a few variables imbalanced. And after we do matching, here we imposed a caliper and we match on propensity scores. So after that, we see that the standardized mean difference is much improved. All of them is below 0.1. So this is an example to assess balance. And the caliper 0.2 means that if we can't find a match with propensity score difference within 0.2, then that treated individual is discarded. So therefore, you see that here we only have 1996 individuals in the treatment group after the match, but we have over 2,000 in the treated group in the original sample. Another way is to do the plot. It's essentially just visualizing the table we just saw. Right? You have the SMD before matching and you have the SMD after matching. So nothing special here. Any questions for these plots and assessing balance in general? Okay, if none, then let's move on to analysis for matched sample. So you see that all of today's, all the things that we talked about for matching is kind of intuitive and applied. We're not doing any theory, partly because the theory is very difficult and I don't know the theory very well, but partly because the application is so common. And I want to have all of you aware of how to do the applied data analysis using matching, so that it might be useful for your future research. Okay, so how do we do analysis after matching? The way to do it is just like what you would do in analyzing a simply randomized experiment. Because we have as if simply randomized treatment assignment in the matched sample. So remember when we were talking about simply randomized experiments, we can use different ways to analyze the data. We can do the unadjusted estimator, right? Calculate the group mean difference. Or we can do regression adjustment. And we have seen that doing regression adjustment can improve on the efficiency and it's robust against misspecified regression models. So similar idea applies here for matching. So I guess the key point that I want you to remember is that although in the matching procedure, we are kind of constructing a data set by finding a treatment, finding a control that looks just as the treated. We're not trying to compete with modeling. We're not trying to say that, oh, after this matching, we have these two columns, the treated outcomes and the control outcomes, just calculate the difference and that's it. But rather, the two methods, the matching method and regression adjustments or some other modeling approaches, they actually work the best in combination. And the rationale behind it is also similar to what we've seen in simply randomized experiments. And that's because, after matching, unless we have perfect exact match, in which case regression adjustment does nothing. But otherwise, there are still chance imbalances after matching. There are still residual imbalances that matching is not able to resolve. So regression adjustment adjusts for this kind of imbalances and therefore improves the estimation result. Now, in talking about the matching, the details of implementing a matching, we discussed a variety of considerations. So the detailed analysis method actually would depend on exactly which matching method you use. Do you use one-to-one? Do you use K-to-1? Do you use variable ratio? Do you use with or without replacement, etc.? So this is a nice review paper that has a lot of these references to different types of methods. So if you encounter a particular method in research, you can check out this paper. For today, we'll look at analysis methods. Yes.
Yeah, I don't really understand what the regression is. So if you match, so let's say you had a set of covariates X and then you match with people one-to-one on it, you would have, person one matched to person two, whatever. And I mean, it would make sense to then compute, like the difference in the outcomes. But are you doing another regression with the same covariates you just matched on? I don't understand what's going on.
Okay, good question. We'll see a little bit more detail on the next few slides, but I guess the idea is that the short answer to your question is you don't have to match on the same covariates, because even if you don't regress any covariate, you still get consistent estimators in the matched sample. But having additional covariates in the regression helps in terms of efficiency and reducing small sample bias. But we'll see some more details here. Okay, so K-to-1 matching, or if it helps, think about a one-to-one matching on this slide. So after K-to-1 matching, if we have good match, then data is like a simply randomized experiment. And therefore we can use methods like this to estimate the causal effect. So for example, if we fit a model with A and all the covariates, or maybe some of the covariates, it doesn't matter. As we've shown, the functional form for this part does not matter when doing regression adjustment for randomized experiments. So then in this case, beta A hat would be the estimated ATT. And why is it ATT, not ATE? This is because in the matched sample, the covariate distribution equals that of the treated group. Here we're matching by using treated group as a reference. And therefore we are estimating ATT, not ATE. So this is a very, I guess, simple example or kind of straightforward example. But this is not the full story. So in fact, there are a lot of debates in terms of the exact analysis method to use for matching. And in particular, here are the two debates. One is, do we use paired analysis or unpaired analysis? The second one is how do we do variance estimation? We'll delve a little bit more into details of these two debates on the next two slides. But here I first want to tell you that I don't think the debates are resolved yet in the literature, but anyway, people are using these matching methods widely in, especially in the applied scientific applications. So, so after discussing these debates, I'll try to provide some of my own recommendations. But when you actually do research, when you actually want to apply, for example, matching in understanding a causal effect of something, I would highly encourage you to read more beyond what's discussed in class to have a better understanding of what you're really doing. Okay, so the first debate, paired or unpaired analysis. The key point in the debate is that should we view individuals in the matched sample as independent from each other? Right. So if we do paired analysis, for example, a paired t-test, looking at each matched pair as a pair, a treated and control, then we can do a paired t-test. Or a kind of similar approach is that we can do a GEE, generalized estimating equation, when looking at data as a clustered data, where each matched pair is a cluster. So these are the methods that, considering the matched sample not as independent individuals, but clustered or paired individuals. Now, there are also arguments for doing unpaired analyses. So what are the examples of unpaired analyses? For example, we can do unpaired t-test, or we can do linear regression without the GEE part, right? GEE essentially is linear regression, but with some kind of within cluster covariance matrix. So there are these debates in the literature, and I don't really know who is right. So what I can do is that I present these to you, and when you're using the method, you can look into it to know more about it. So that's for that. And the second debate is how to do variance estimation. Okay, so the key point in the debate is that, so first, should the uncertainty in the propensity score or the matching procedure be taken into account? And the second question is, if yes, how? Now, again, there are different ways in the literature that people analyze matching data. So I guess maybe that's why I was very vague when first describing the analysis method and kind of why Roy asked his question. So here are what different people do different things. So some use methods for analyzing randomized experiments. What that means is that they're considering the propensity scores to be known. Or in other words, after a matched sample is constructed, they're kind of treating this as they're doing the analysis conditional on this particular match. Some would argue that one can use bootstrap to assess the uncertainty. So looking at the entire data, original data before match, we can do bootstrap. We can subsample with replacement the entire data, then do matching, then do analysis. We replicate this multiple times to understand the uncertainty of the estimator. This is a different perspective. Now, better yet, some argue that bootstrap doesn't work in this situation. Why it doesn't work? Because of the non-smoothness of the matching procedure. So if you have looked into the theory of bootstraps, you will see that the asymptotic theory for bootstrap requires the functional that you're bootstrapping to be smooth. So, but in this case, when you're doing subsample, if you change one individual in the subsample, then maybe many of the matches will be changed. Right? It may have very big influence. So this is kind of the intuitive idea of why we have this non-smoothness phenomenon. And these two authors wrote some very hard to read econometrical papers, try to argue that bootstrap doesn't work, and they derived asymptotic distribution for the matching estimators. But others don't, other literature don't agree with them. So I don't know who is right, but finally, another reference is that in this Inference and Rubin book, chapter 19, there are some theoretical results for the variance estimator for some simple cases. So you can check it out if you're interested in. Okay, so finally, my recommendation. My recommendation is that I don't know who is right. Very likely because I don't know the literature well enough. Unlike marginal structural models and stuff, I have done research in that. So I know a lot of these proofs. I can do that in class and show you the proof. But for matching, on one hand, the proof is much more difficult. It's not just estimating equations. So anyway, I don't know who is right. And in addition, given the large variety of the matching methods and the fact that different authors focus on different matching methods when they're arguing for something or arguing against for some method, it's unclear if there is a universal answer in terms of should we do paired or unpaired analyses, should we do bootstrap or not, etc. And here are practical recommendations. I'll let you go after I went through this. So first, these are ordered in terms of the level of sophistication or effort that you need to spend on. First, I would want you to be aware of these debates. And second, if you're doing an applied data analysis using this type of method, maybe it's a good idea to find some similar papers in terms of the particular matching method they use and see what these people use in terms of analysis methods. And third, we can sometimes also rely on the choice of widely used packages. So in the R code, I have included some R packages, and they use particular variance estimations from, I believe, is from this paper, from this Abadi and Imbens paper. So anyway, that's another way to determine what's the choice. And then finally, if you really want to get into this issue, then read some of the debates and better yet, do some simulations to see if which method works for your particular problem. Okay, so this is what we have talked about today for the matching. And the next time we'll switch gear to look at causal graphs and confounding variables. So we won't go through the code, the R code in class, but it's posted online. So feel free to look at it at your own time. Thank you all, and I'll stick around for 10 more minutes.